Our first step for this problem is going to be to balance this chemical reaction because this chemical reaction right here is not balanced. So the first thing that you need to do is you need to pause the video and practice your balancing of chemical reactions and then come back and see if you balanced it correctly. So to correctly balance this, we have 4 moles of aluminum oxide react with 9 moles of iron, and that's going to produce 3 moles of iron oxide and 8 moles of aluminum. Now we're ready to move on to the problem. We have 25.4 grams of aluminum oxide. So that's going to be this guy right here. And that's going to react with 10.2 grams of iron. But we're not going to have enough of one of these. So our goal is to find the limiting reactant. So remember that what we're going to do is we're going to go from our grams of aluminum oxide and we're going to find out how much of a product is made. Now, I am going to notice something. I'm going to notice that I'm later asked to find the number of moles of aluminum. So guess what? I'm going to find out how many moles of aluminum that many grams of aluminum oxide make. Then I'm going to take my grams of iron that I'm given and I'm going to find out how many moles of aluminum that's going to make. Once I find whichever one is less, that's going to be my limiting reagent. So let's get started. We have 25.4 grams of aluminum oxide. Remember, our first thing is going to be finding out how many moles of aluminum we have. So I'm going to put grams of aluminum oxide on the bottom because I don't want that anymore. And I'm going to put moles of aluminum on the top because that's what I want to find out. Well, the moles of aluminum is pretty easy. The moles of aluminum is right here. 8 moles of aluminum. My balance reaction tells me that. So I'm going to go ahead and put that right there. The harder part is figuring out what the balance reaction tells me about grams of aluminum oxide. So according to my balance reaction, I need 4 moles of aluminum oxide. So I can calculate how much 1 mole of aluminum oxide weighs. And then once I know how much 1 mole of it weighs, I'm going to multiply that by 4 because my balanced chemical reaction here says that I need 4 moles of it. Once I've got that, I'm going to put that as my bottom mass. So take a minute, pause the video, see if you can calculate the correct molar mass of aluminum oxide, multiply it by 4, and then unpause the video and come back and see if you got the same thing as me. So 1 mole of aluminum oxide would weigh 101.96 grams. If I multiply that by 4, that means that 407.84 grams of aluminum oxide are necessary. So now I can solve for my problem. I now can find out how many moles of aluminum that's going to make. And when I solve this mathematically, I get 0.498 moles of aluminum. All right, let's move on to our iron. We're told we've got 10.2 grams of iron. But again, I don't want to know about grams of iron. I want to know about how many moles of aluminum is that going to make. Well, my balanced equation tells me 8 moles of aluminum. That one's easy. My balanced equation only tells me about how many moles of iron. It doesn't tell me how many grams of iron. So I'm going to go ahead and I'm going to find out how much 1 mole of iron weighs by looking on my periodic table. And I see it's 55.85 grams. Well, the balanced equation says that I have 9 moles of it. So I'm going to multiply that by 9, which means that my balanced equation tells me I need 502.65 grams of iron. Take a minute, pause the video, and see if you can calculate how many moles of aluminum this would be. According to my calculations, I get 0.162 moles. So now I got to figure out what's my limiting reactant. Well, remember, the limiting reactant is whichever one is going to make me less moles of aluminum. So that's going to be my iron right here. Iron's going to make me only 0.0162 grams of aluminum. I'm not going to be able to make 0.498 moles of aluminum because I don't have enough iron to make that much. So I'm only going to make 0.162 moles of aluminum. Iron is my limiting reactant. So iron limits me. Well, it says determine the number of moles. Well, I now figured that out. I figured out that I can't make this many. So how many moles of aluminum am I going to make? I am going to be able to make 0.162 moles of aluminum. So we know that iron limits us, and we know that we're only going to be able to make 0.162 moles of aluminum. So we're not going to use any of the 25.4 grams of aluminum because we're not going to be using all of that. We do know we're going to use all 10.2 grams of iron. We do know we're going to make this much aluminum. So the next question says, how many grams of iron oxide will be produced? Well, we can go from our 10.2 grams of iron and find out how many grams of this are made. Or we also know we're going to make this much aluminum. So we could go from aluminum to grams of iron oxide. So I could do this problem two ways, and I will show you how to do both of them. You could start with your 10.2 grams of iron, and we don't want grams of iron anymore. We want to find out how many grams of iron oxide we're going to make. So we could solve it like that. The other way that we could solve this problem is that we could take the other piece of information we know, which is that we're going to make 1.62 moles of aluminum. And since we don't want moles of aluminum, we're going to put that on the bottom. And we want to figure out how many grams of iron oxide we're going to make. So we put that on the top. So pause the video for a second and see if you can figure out either way of doing this. You could do both ways, or you could do just one way. But pause it and see if you can figure it out. So according to my balanced reaction, I need 9 moles of iron. Well, if you remember from the previous problem, 9 moles of iron was 502.65 grams. So that would go down there on the bottom. We also know how many moles of aluminum it's going to make. From our balanced reaction, we know 8 moles of aluminum are needed. So to solve either of these two problems, the only other piece of information I need is about the iron oxide. So first thing I need to do is find out how much does 1 mole of Fe3O4 weigh. When I calculate that, I find that it weighs 231.5 grams per mole. But our balanced equation says that we need 3 of them, 3 moles. So we're going to multiply that by 3, which means that 3 moles of it would weigh 694.5 grams. So that's what number I'm going to put on the top for either of the ways that I tried to solve this problem. If I solve it using my 10.2 grams of iron, I get 14.09 grams of Fe3O4 are going to be made. If I solve it using my moles of aluminum, I get that 14.06 grams of Fe3O4 are made. Notice these are extremely similar to one another. So I'm going to make right around 14.09, 14.06 grams of iron oxide. So how many grams of excess are we going to have left over? Well, iron limits us, so we're going to use all of iron. That means that we're going to have some leftover aluminum oxide here. So we're going to need to figure out how many grams of aluminum oxide are we going to need to use. Well, we already know a number of things. We already know we're going to use all 10.2 grams of iron. We already know we're going to make 0.162 moles of aluminum. We already know we're going to make this many grams of iron oxide. We can actually solve for grams of aluminum oxide from all 3 of those, but we only have to do it once. So we want to go from one of the things we know to how many grams of aluminum oxide do we need. So I'm going to go ahead and I'm going to use the 10.2 grams of iron. And I'm going to figure out how many grams of aluminum oxide am I going to need to do that. So if I start with my 10.2 grams of iron, I already know from the problem above that I need 502.65 grams of iron. What I need to find out is how many grams of aluminum oxide do I need. So I'm going to look at aluminum oxide over here, and I see that according to my balanced equation, I need 4 moles of aluminum oxide. Well, I need to figure out how many grams that is going to be. Well, 1 mole of aluminum oxide weighs 101.96 grams, but we need 4 moles. So I'm going to multiply that by 4. So according to my balanced equation, I need 407.84 grams. So I can solve it like that. I could also take my 0.162 moles of aluminum, and again, I know that I need 8 moles of aluminum, but I need to find out how many grams of aluminum oxide do I need. Well, I just figured that out. I need 407.84 grams of it, and I could solve for that way. I could also take my 14.09 grams of iron 3 oxide, and I can solve for my grams of aluminum oxide. Well, 407.84 grams. How many grams of iron oxide? Well, according to my previous problem, looks like 694.5. So I can solve that way. Any way you do it. If I do it the first way, I get 8.27 grams of aluminum oxide. If I solve it the second way, I get 8.26 grams of aluminum oxide. If I solve it the third way, I get 8.27 grams of aluminum oxide. Notice how they're all the same. Because I know I'm going to use 10 grams of iron, so that's going to have me use this many grams of aluminum oxide. I know I'm going to make 0.162 moles of aluminum, so I'm going to need 8.26 grams of aluminum oxide. Well, here's what the question is asking me. Determine the number of grams of excess reagent. Well, remember that up here it says we've got 25.4 grams of it. We're not going to use all of it. So let's find out how much we've got left. 25.4 grams minus the 8.27 grams that we know we're going to use. Well, that means we're going to have 17.14 grams of aluminum oxide left over because we're only going to use 8.27 grams of it. So that is how much we have left. I'd like you to try this one on your own. For my answers, I am going to go from 25 grams of sodium chloride, and I'm going to calculate how much sodium phosphate I need. And then I'm going to go from 85 grams of barium phosphate, which is this one, and find out how many grams of sodium phosphate are made. And then I'm going to compare those two to find out which one is my limiting reactant. So grams of NaCl to grams of Na3PO4, grams of barium phosphate to grams of Na3PO4. Try that first step on your own, pause the video, and then come back. So these are the two materials that you should be starting with. For my grams of NaCl, I'm going to put grams of NaCl on the bottom, and then I'm going to put the grams that I want to find of sodium phosphate on the top. Now, to find my grams of NaCl, I'm going to find that 1 mole of NaCl has a mass of 58.44 grams, but this has 6 moles, so I'm going to multiply that by 6. So that means that there are 350.64 grams of NaCl in this problem. Now for Na3PO4, I'm going to find 1 mole of Na3PO4 has a mass of 163.94 grams, but there are 2 moles, so I'm going to multiply that by 2. So that means that my mass is 327.88 grams. Then I'm going to solve for my grams of sodium phosphate of that product that is made. For this one, I get 23.38 grams. Now I'm going to do the same thing with the other reactant, the barium phosphate. So for barium phosphate, 1 mole of barium phosphate has a mass of 601.93 grams. There is only 1 mole because there's no coefficient in front, so that means that on the bottom, I'm going to put 601.93 grams of barium phosphate because I don't want barium phosphate. Now, the same number, 327.88 grams of sodium phosphate, are going to go on top because that's the same material. I want to make sure that I'm going to the same product for each of my reactants. And so I find that that much of the reactant of barium phosphate can make 46.3 grams of sodium phosphate. So now I'm comparing these two. Remember, your limiting reactant is the one that only can make less. So that's going to be this one, is the one that can make less of it. So that means that my limiting reactant is my 25 grams of sodium chloride. So that's limiting me, okay? Now, that means that I'm going to have excess barium phosphate left. So it wants to know, well, how many grams of excess are going to be left? So in order to solve that problem, what we're going to need to do is we need to find out how many grams of barium phosphate do we need. So I can go with anything I know is going to be used up. I know that I'm going to use up all 25 grams of NaCl. I know that I'm going to make this many grams of sodium phosphate. So I can either go from my 25 grams of NaCl to my barium phosphate, or I can go from my 23.38 grams of sodium phosphate and convert to grams of barium phosphate. I will do both ways so that you can see and then compare both of them so that we know how many grams of excess are left. Pause the video and try to do either one of these two ways on your own, and then come back and check your answer. So I've got both of my ways set up here. I can either go from my 25 grams of NaCl, or I can go from the 23.38 grams of sodium phosphate that I know I'm going to make. So I went ahead and I set my grams of NaCl on the bottom. I set my grams of Na3PO4 on the bottom. I know from the previous problem that I need 350.64 grams of NaCl, so I went ahead and put that in. I also know from the previous problem that my grams of Na3PO4 is 327.88 grams. Now remember, what we're trying to find is how many grams of our excess are we going to be having left. So we want to find out how many grams of this 85 grams of barium phosphate am I given. So we're going to put that on the top because we want to figure out how many grams of barium phosphate are we actually going to use. And I already know that my balanced equation says that I need 601.93 grams. So I can go ahead and put that on the top there. So when I solve for both of these problems, you can see you get the same thing. This is how much barium phosphate is going to be needed to react with that 25 grams of sodium chloride that we know is limiting us, or that's how many grams we know is going to be used to create that much product. That's the amount of product we know we're going to be making. So we can see this is how much that we are going to be using, but we were given 85 grams of it. So it wants to know how many grams of excess are left. So the last step is simply to subtract. If we take our 85 grams and subtract the 42.92 grams that we are going to use, then we find that we will have 42.08 grams of it left for our excess. Now you can stop here. I do have one more practice problem if you want to try and pause and do the whole next one on your own, and then come back and see if you can do it, or you can follow along with me step by step. So this problem does not require you to find the limiting reactant. It says a chemist burns 160 grams of aluminum. So that's going to be this material here. And it says that there's excess air, so plenty of oxygen is going to be there. So nothing's limiting us. And she's producing aluminum oxide. When she's done with the experiment, she finds that she produces 260 grams of solid aluminum oxide. So she's making 260 grams of this guy. It says to determine the theoretical yield. So what that means is how much of the aluminum oxide should get produced from 160 grams of aluminum. This is how much was actually made, but that's not always necessarily 100% yield and exactly the amount that's supposed to be produced. So what we're going to do with this problem is we're going to start with 160 grams of aluminum. And what we want to do is we want to find out how many grams of aluminum oxide should have been made. So on the bottom, we're going to put grams of aluminum because we don't want grams of aluminum anymore. And remember, we create our conversion factor here by looking at the balanced equation. So if I look at aluminum, it says that I need 4 moles of aluminum. So I'm going to calculate how much would 4 moles of aluminum weigh, and I'm going to put it right here. Then it says that I need 2 moles of aluminum oxide. So I'm going to calculate how much 1 mole weighs. I'm going to multiply it by 2 and put it right there. Pause for a second and see if you can calculate that. So I looked on the periodic table, 1 mole of aluminum weighs 26.98 grams, multiply it by 4, that comes out to 107.92 grams. Then 1 mole of aluminum oxide weighs 101.96 grams, multiply that by 2 because we have 2 moles of it, that comes out to 203.92 grams. Now solving this problem is going to tell me how many grams of aluminum oxide I should have gotten. And based on my calculations, I should have gotten 302.33 grams. So you can see how the scientist, the chemist, produced it 260 grams, but she should have gotten 302.33 grams. So she wasn't quite at 100%. We could actually also calculate the percent yield by taking the amount that she got and dividing it by the amount that she should have gotten, and then multiplying that by 100, and then we could find the percentage yield. So she actually did pretty good with around 86% yield there. Now, the next question says, how many grams of excess reactant are left? So, since she only made 260 grams of aluminum oxide, let's find out, because she didn't make exactly what she was supposed to, let's find out how many grams of aluminum that much would require. So, we're going to put our grams of aluminum oxide on the bottom, which according to our balanced equation, we need 203.92 grams, and aluminum would be 107.92. So we're going to calculate based on the fact that she only made 260 grams of aluminum oxide. Let's find out how much aluminum would be used making that much product. So if she made 260 and was supposed to make 302, that much aluminum, the amount of aluminum that would be needed to make 260 is going to be 137.6 grams of aluminum would be needed to make that much of the product that she made. So that means, remember, she had 160 grams of aluminum, but only 137.6 grams would actually be needed to make the amount that she made. So that means that there is some of her reactant that didn't react, some of her aluminum didn't react. So if we subtract those, we find that 22.4 grams of her aluminum did not react. This is a great practice problem for limiting reactants. We've got 4,000 grams of heptane, which is going to be this material right here, C7H16, and we want to find out if it gets combusted with 7,000 grams of oxygen, which of those two materials is going to be limiting us. So remember, we're going to start with the 4,000 grams of heptane, and we're going to go to one product. Now, it doesn't matter if you go to the product of carbon dioxide or the product of water, but for both of these reactants, you have to go to the same one. Now, I know that the molar mass of water off the top of my head is 18.02, so I'm going to go to water for my examples. So pause the video and try to do it on yourself. Go from 4,000 grams of this and find out how much water is going to be made. Then go to 7,000 grams of oxygen, find out how much water is going to be made, and remember, whichever one is less is the one that is going to be limiting you. So this is what your basic setup should look like. And next we need to find out how much does 1 mole of heptane weigh. 1 mole of oxygen, I know off the top of my head, is 32 grams. I also know that 1 mole of water is 18.02 grams. Now, remember the balanced equation tells us how many moles, so we're going to have to multiply those masses to find out the correct number of masses from the balanced equation. So I have the correct number of grams. I took 32, multiplied it by 11, 18.02, multiplied it by 8, and now I can go ahead and plug these numbers into where they belong. So I am going to put in my 100.21 grams of C7H16. I'm going to put in my 256 grams of oxygen, and I'm going to put in my 144.16 grams of water, and I'm going to solve and see which one is less. And so I see that oxygen is going to be my limiting reactant because I make less of it. So my answer to my question is oxygen is my limiting reactant.